as it was in the beginning, and R6 is 1 kilo ohm. So my very last equivalent circuit has a 12 volt battery and a single resistor. I'll call that RD. And RD's value is 1 plus 5 is 6 plus 3.5. So that's 9.5 kilo ohms. Now what's important to understand is this. This resistor doesn't actually exist. It's imagined. However, its value is equivalent to the total resistance across our original circuit. Because it's equivalent, the current going through this imagined resistor is the same as the current that would go through the original circuit. I'm going to simply use V equals IR. That's Ohm's law. I know my potential, my V, is 12 volts, and R is 9.5. So I is 12 divided by 9.5. So the current going through this imaginary resistor here is 12 volts divided by 9.5 kilo ohms. And that gives me 0.00126 amps. If you're not getting exactly that, perhaps you forgot to divide by 1,000. That kilo ohms means we have 1,000 ohms. So if I want to report my answer in amps, then I have to have these decimals ahead of time. So I did 12 divided by 9.5 and then divided by 1,000 to deal with that K. Okay, now that I have the current going through here, by inspection, since this is equivalent, whatever current is going through this imaginary resistor is the same as the current that's coming out of this battery and flowing back into it. The current that flows here will branch off two ways, so I don't know the individual currents here or here, but it is all going through R1 and it's all going through R6. So the current that I have here, the 0.00126 amps, has to be the current through R1 and the current through R6. So I'm going to come back to my table and say that R1 and R6 both have the value 0.00126 for their current. Now again, I'm going to use Ohm's law, V equals IR, and the voltage is current times resistance. So for resistor 1 and resistor 6, the voltage is going to simply be this number times that. So I have 5,000 times 0.00126, 6.3 volts. And here I have 1,000 times 0.00126, 1.26 volts. Now look at RC. So the strategy is this. We start with a complicated circuit. Okay, so I started here. We make simpler and simpler circuits to find one piece of information. We're then going to take that piece of information and bring it back up to the less simplified and less simplified circuits to fill in more pieces of information. We've determined that the current is 0.00126 amps through here. That will be the same current that goes through RC. If its current is 0.00126, then the electrical potential, or the voltage from here to here, is going to be that current times its resistance value of 3.5 kilo ohms. So we have 3.5 kiloohms. And we multiply it by 0.00126. Gives us 4.41 volts. Now remember, RC doesn't actually exist, but it takes the place of RA and RB in parallel, who in turn also don't exist. However, because it takes the place of them, if the voltage across here is 4.41, the voltage across each of these would also be 4.41. I can use Ohm's law again, take this voltage, divide it by this resistance to find the individual currents here and here. If you know this well, you'll know by symmetry, you just take the original current and divide it by 2. This is symmetrical because the resistors are identical. I'm going through this because, well, if you knew that, you wouldn't be watching this video. Okay, so this is 4.41 volts, and we're dividing by 7,000. Giving us current here of 0.00063, and that's going to be the same here as it is here. The current through each of these branches is going to be the same as the current through each of these branches. So that means I now know R2, 3, 4, and 5 all have the currents 0.00063, which incidentally is exactly half of that. Half of this, right? And now that we know the current through each of these resistors, again with Ohm's law, all we need to do is multiply that current by the resistance to find the respective voltage.